Hello everyone, welcome back to Physics 331. In the last video, what I tried to do was to do a demonstration of the non-ideal properties of transmission lines. And so specifically what we looked at was the transfer of power through a long transmission line as a function of frequency. And what we found is that when we were using 8-meter long coaxial cable and operating at a frequency of about 6 gigahertz, I think only about 1% of the power incident at one end of the transmission line was received at the opposite end. And so that was a demonstration of power absorption along the length of this transmission line. I wanted to follow that up with a second video demonstrating some other effects of transmission lines. First, what we'll look at is the propagation of pulses along a transmission line. And so let's see if this will let me advance my slides. Here we go. So one thing I wanted to first mention before we get to the demonstration is that what we talked about in the lectures when we were discussing transmission lines is kind of thinking of the transmission line as a cascaded series of these LC branches. So an inductance per unit length and a capacitance per unit length. And we had these branches follow each other one after another. We isolated one of those branches and we analyzed it, and we eventually ended up at the wave equation for both the voltage and current of the transmission line. And in order to, that wave equation mixed, it was a partial differential equation that involved both position and time. And in order to make progress, what we did is we assumed a harmonic time dependence for the voltage and current. This allowed us to evaluate the integrals because we could evaluate the time derivatives. So if we take the derivative of e to the j omega t, we just get a j omega coming down and times that original exponential. And once we evaluated those derivatives, we could then cancel all the factors of e to the j omega t in all of the terms. And that simplified things quite a bit, because then we had a differential equation only in position. And so what we actually solved for was the position dependence of the voltage amplitude and the current amplitude. So what I wanted to ask then is, well, what if we were dealing with voltages and currents that were not sinusoidal, not harmonic? Do we have to start from scratch? And the answer is going to be no. So what we're going to do is we're going to take some of what we learned from our analysis of time harmonic signals and then apply some of what we're talking about now with Fourier transforms, and we'll be able to deduce the behavior of transmission lines in the presence of signals that are not sinusoidal. So this is kind of a bit of a preview for some of the things that we'll be able to look at once we finish our discussion of Fourier transforms. Okay, so the experimental setup is quite simple. What we're going to have is a pulse generator. So it'll produce a narrow pulse in time. And then at the output of the pulse generator, we'll have an oscilloscope attached. And then we're going to connect a long transmission line at that input to the oscilloscope. The transmission line, again, is about 8 meters long. One thing that I should tell you is that the output impedance of the pulse generator is 50 ohms, and that's matched to the characteristic impedance of the transmission line. So the actual experimental setup is here. So this is the setup that I have in front of me. Here's our pulse generator. This is just a trigger output going to channel 2 of the oscilloscope. So that's used only for triggering the oscilloscope. It has nothing to do with the data that we're going to collect. The actual pulses are output here. the output of the pulse generator goes to channel 1 of the oscilloscope, and then there's a little T connector where we can connect a long coaxial cable. So this is a coaxial cable that is, like I said, it's about 8 meters long, and it has a copper outer conductor, and then the center conductor is a piece of steel that has a copper cladding, so an outer layer of copper, and then it's plated with silver. Okay. The other thing I can do is I connect different load terminations to the end of the transmission line. And so I can have the transmission line just open, so nothing connecting the center conductor to the outer conductor. I can connect a short circuit, so just have a wire that connects directly from outer conductor to center conductor, or I can connect 50 ohms between the outer conductor and center conductor. Okay, and so the width of the pulses that are going to be generated by this pulse generator is, approximately 25 nanoseconds. Okay, so I have here a little program that I've written that's going to talk to the oscilloscope, and it's just going to show us what is on channel 1 of the oscilloscope. So I'm just going to get this running. And so here we go. Right now, I don't have the coaxial cable connected at all. This is just directly from the output of the pulse generator directly into channel 1 of the oscilloscope. And so here's the output pulse. Okay, so what we'll do now is I'm just going to take my long coaxial cable, connect it also to channel 1 using that T connector that I showed you. And then the far end of the coaxial cable is just open. It's an open circuit. There's nothing connecting center conductor to outer conductor. And we'll see what we get. Okay, and so there it is. And so we get these two pulses. What I think we can intuitively understand what is happening. We have our first initial pulse that is incident from the pulse generator, and then that propagates along the length of the transmission line, reaches the open circuit at the end, and is reflected, and then comes back down the transmission line in the opposite direction, reaches channel 1 of the oscilloscope again, and so we get this second pulse, which is the reflected pulse. Maybe you could notice that the reflected pulse is a little bit smaller in amplitude than the initial pulse, and so that's an effect of, again, some of the losses along the length of the transmission line that we saw in the last demonstration. Okay. What I can do with this program is I can press this capture button, and it'll take like a screenshot or a snapshot of the current display on the oscilloscope. So I'll capture that. And that captured waveform is the red one. So the red waveform is a static image, and then the blue one is a live display of what's on the oscilloscope. Okay, so let's just go back to this presentation, and I will go now to the next slide. So all I'm going to do is now, instead of leaving the transmission line open at the far end, I'm going to connect a short circuit across it. So I'm going to connect a wire that connects the center conductor of the coaxial cable directly to the outer conductor. Okay, and so we'll go back to this image. Remember, the red line is a capture of a static image of what we had, and then the blue line is the live waveform. And so I'll put the short circuit on now, and we'll get this screen to update. And so now what we see is that the incident pulse is basically the same. It looks like there's some small offset difference, but other than that, the input is exactly the same. The reflected pulse comes back at the exact same time. It's just inverted. Okay, and so that's an interesting observation. What I'm going to do is I'll go back to this presentation and we'll advance this slide. The last thing I can do is I can take off that short circuit and put in a 50 ohm load at the end of the transmission line, and that 50 ohm load will match the characteristic impedance of the coaxial cable. Okay, and so if I take off the short circuit, we should get back to our original captured waveform. And now I'll put in the 50 ohm loads. And what we get is that there's no reflected pulse at all anymore. And so we have just the incident pulse from the function generator, and then we don't see any reflected pulse. If you think back to some of the other results that we've had from our analysis of transmission lines, we had the reflection coefficient, which was determined by the load impedance minus the characteristic impedance of the transmission line. So it would have been like ZL minus Z0 divided by ZL plus Z0. And so if you think of that for the case of an open circuit, the load impedance is basically infinity. And so the ZL in the numerator and denominator would both dominate Z0, and you'd expect the ratio of those quantities to be +1, so a reflection of +1. Then if you think of the case where ZL is equal to 0, a short circuit, then you'd have 0 minus Z0 divided by 0 plus Z0, and the ratio would be -1. And so that inverted pulse, that inverted reflected pulse that we saw is a result of that -1 in the reflection coefficient. So that -1 inverts the pulse upon reflection. And then if you think of the case where ZL is 50 ohms or equal to Z0, in the numerator we would have ZL minus Z0 is equal to 0, and so there's no reflection. And so that's consistent with those types of observations. But those observations that analysis was all done for harmonic signals, so signals that had a sinusoidal time dependence. And so we haven't yet calculated any results for input signals that are not sinusoidal. And so what I hope we'll be able to do is, after our discussion of Fourier transforms, come back and revisit transmission lines and see if we can understand some of these observations that we just saw. Okay, so let me go back to this presentation, and I'm going to show you one more thing. So this is, I'm going to call this a transient response. And so a transient response really means that you're going to take your system from one equilibrium or one steady state and make a change and watch the system evolve into a new equilibrium or a new steady state. And so how does the system evolve from one equilibrium to another? Okay. So the experimental setup is similar with a couple of important differences. One of the important differences is that instead of having a short pulse, what I'm going to do is I'm going to allow the voltage to step from 0 to some non-zero value. And so that's going to be the change in our system that causes the evolution from one equilibrium to another. So one equilibrium is established when the voltage is at 0, and then we step the input voltage to some non-zero value, and we watch the system evolve to that new equilibrium. The other difference is that instead of having the output of our signal generator go directly to channel 1 of the oscilloscope, I'm going to insert a 1 kilo ohm resistor between the two. Okay, and so other than that, everything will be the same. I think I can show you a picture of the experimental setup. And so we have the same pulse generator, but instead of having it set to output narrow pulses, we'll have it set to output a step in voltage from 0 to some non-zero value. And then we have a little box at the input of our oscilloscope, the channel 1 input. And inside that box, there's nothing more than just a 1 kilo ohm resistor. Okay, good. So I'll get back to this LabVIEW program. And so what I'm going to do is I'm going to stop it and restart it. Okay, and so right now I still have it set up with the without the 1 kilo ohm resistor. It's still, the pulse generator is still outputting a narrow pulse, and I still have the 50 ohm resistor on there. So the first thing I'll do is take off this 50 ohm resistor, so our reflected pulse comes back. And now what I'm going to do is I'm going to make the input pulse really long. So let me just disconnect the transmission line. And so this just shows you now what is coming out of the pulse generator with nothing connected to it, no transmission line. And so it just starts with 0 or some low voltage, and then there's a sharp transition to some higher voltage. It looks like it's about 7.5 volts. Okay, so what I'm going to do is I'm going to take our 1 kilo ohm resistor. I'm going to connect that between the output of the pulse generator and the input to channel 1 of the oscilloscope. And then I'll connect our transmission line across there. And now I'm just going to fine-tune some of the settings of the oscilloscope so that we can see some of the detailed shape. Okay, let me Okay, here we go. And so this, where the output of the function generator or pulse generator abruptly changes from 0 to some non-zero value is right here. And then what you see is this really distinct staircase sequence of changes in the voltage. In fact, what I might do is I might try to turn on the averaging function to the oscilloscope, and we might be able to clean that up just a little bit. And so you can see this really distinct staircase type behavior. And if I change this a little bit more, expand the time range. So in addition to the staircase kind of behavior, notice that the height in subsequent steps gets smaller and smaller. So those steps are still existing out here. They're just really small so that they're beyond the resolution of the measurement. And so in addition to that staircase, you kind of have this exponential approach to some new equilibrium. And so those are the two main observations that we can make. And again, that's a behavior that's, pretty complicated for what's really quite a simple experimental setup. It's just a long transmission line and a 1 kilo ohm resistor, and then we hit the input of that with a voltage step. Just to finish things off, I'll show you one more thing. I'm going to, right now, our transmission line just has an open circuit at its far end. And so I'm just going to insert that short circuit, and we'll see how that changes things. And so there's the short circuit, and let me just see if I can expand the scale here we might be able to clean that up a little bit. Yeah. There you go. And so there's another kind of pretty exotic type behavior, right? Something that's kind of maybe not intuitive unless you've really studied transmission lines for a long time. Finally, just to end things, I'll put the 50 ohm load at the end of the transmission line. And when I do that, we just get one step. So here's where the output of the pulse generator transitions from 0 to a non-zero value, and then we get some step in voltage that is much smaller than the voltage step of the output of the pulse generator. So I think the voltage step of the output was something like 7.5 volts, I think, and so we get only a small fraction of that. Okay, so hopefully what we'll be able to do is, I don't think we'll analyze all of these different cases, but maybe once we've finished our discussion of Fourier transforms, I think something we could analyze pretty readily will be the pulse propagation demonstration that we saw. All right, so thank you very much, and I will talk to you next time.